Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic of this video is Rayleigh flow, and the sections in the textbook are 17.6 and 17.7. So here are the learning outcomes. At the end of this, you will recognize the correct mass, momentum, and energy balance that's applicable to heating of a high-velocity flow. So what I mean is something like what we're calling compressible flow, something that's near sonic, supersonic, in that range. You'll understand the qualitative behavior of heat addition or removal from a sub or supersonic flow, and you'll be able to use the Rayleigh flow table to solve a problem involving heating of a supersonic flow. So first I just want to talk qualitatively about what happens if we heat a flow that's near sonic velocity. So remember, everything we've looked at so far, we haven't been adding any heat. They've been adiabatic. Now what we're going to be looking at is this picture that I'm showing over here on the right, where we have, for example, say a duct with a high velocity flow, and then we're actually going to add some heat. And so it's going to have some inlet conditions, a pressure and a temperature. Assuming this is an ideal gas, from that we could go ahead and determine the density. And then we'd also be given the velocity. And then the question we want to answer is, if we add some heat, what are our outlet conditions? And so what we're going to be solving is a mass, a momentum, and an energy balance. And so let's go ahead and review those. We've seen them all before already. Here's our mass balance, density times the cross-sectional area and the velocity. So just the inlet equals the outlet for the mass, because we're not adding or removing any mass. That's pretty straightforward. Here's the momentum balance we saw before. And again, A is the cross-sectional area, and this is the pressure. And it turns out what we can do, in this case, the area is constant in both the inlet and the outlet. It's a little different than when we had the nozzle. And so if we go ahead and just divide all of those terms by the area, we can actually get a slightly different form of this equation, which is this here, where now I have the pressure, and now I've got the density times the velocity squared on these two terms here. So that's the momentum balance, just a slightly different form, because with a constant area we've canceled that out. And the last thing is the energy balance, and we've seen this before, except now we have this additional term, we have the heating. And I've written this on a per mass basis, so we have the enthalpy and then the kinetic energy term, and then what we're doing is we're adding some heat, Q dot, and then we're going to look at our outlet conditions. All right, so the only difference really with this from what we looked at before is we have this new term, we've got the heat addition, Q dot, and then in the momentum balance, it's taking a slightly different form. We're able to cancel out the area. And notice in the mass balance up at the top, we can go ahead and cancel out the area as well in both of those. So the area of this is not going to be entering the problem. Okay, so what we want to do now is we want to solve this. And since we have this new variable Q, what that means is we don't know the outlet conditions unless we specify Q. Or turning that around, if I specify the outlet conditions, I could solve for Q. So there's a kind of a new unknown here, which is the amount of heat being added. But that's the only one thing that needs to be specified. And as soon as I specify what Q is, I can determine all of my outlet conditions using these three equations. So qualitatively, that's what we're going to be doing. I want to talk about some interesting behavior for this. Okay, so here what I'm showing is this is all the possible solutions that I could have between subsonic and supersonic flow with some sort of heating. So this is called the Rayleigh curve. So let me just kind of describe what you're looking at here. This is a TS plot, and let's go ahead and look at this upper line over here. It turns out that points over here, like in this area, these are very like kind of slow subsonic flow. Okay, and so all the possible solutions, if I go ahead and solve that mass, momentum, and energy balances, are going to fall in this line. So for example, if I was to add some heat, the temperature would increase, the entropy would increase, I'd be going over and up to the right. So let's kind of talk about the various things that can happen here. So as I said, if I go ahead and heat a subsonic flow, I'm going to go in this direction from this part on the kind of on the upper left of the diagram and moving upward, and I'm going to be going toward Mach 1. So that kind of makes some sense. We've looked at that before. And so if I was to do the alternative, if I was to take a subsonic flow and cool it, I'm just going to go in the opposite direction toward Mach 0, and I'm going to be going down on the curve. So that's what's going on in this upper left-hand portion of the curve. Okay. Now what's interesting is when I start looking at supersonic flow. So for example, supersonic flow is conditions over here on the bottom of the curve, because with supersonic, I'm going to be at lower temperatures. So for now, maybe say I had a supersonic flow down in this condition here, and if I was to go ahead and heat this, what I'm actually going to be doing, I'm going to be increasing the entropy because I'm adding heat. So clearly I'm increasing the entropy, and it means I'm going to go up in this direction. The temperature is going to increase, but I'm going to be going toward Mach 1, so I'm actually slowing it down. So if you heat a supersonic flow, you actually slow it down. And then what even gets a little more interesting is now if I was to do the opposite, remove Q, I would be going down in this direction. So if I have a supersonic flow and I remove heat, it actually goes faster. Temperature drops and I go to a much, much larger Mach number. So sort of counterintuitive, but it's all based on the fact that all the points on this line here, all the possible solutions for various values of Q, with a starting point and an ending point landing on this. Now there's one last point that's particularly interesting, which is what goes on between these points B and A. So remember, I'm heating the fluid as I go up in this direction here. I'm going toward Mach 1. If I'm heating a supersonic flow, I'm going up in this direction toward Mach 1. Where's Mach 1? Well, Mach 1 is right there. It's at point 1. So that right there is a Mach number of 1. So there's this kind of interesting curve here at the top. And what actually happens here is I'm continuing to add heat. I'm heating over here, but if I'm at point B and I heat it, the temperature goes down and the velocity increases. And that's very counterintuitive to heat something and have the temperature go down. Heating it, I'm adding heat all the way up until I get to Mach 1. All right. Now, one of the things to point out, Mach 1 right over here, this is called choked flow. And at this point, I'm heating, I'm going in this direction, I'm going in that clockwise direction. If I'm heating the supersonic flow, I'm going in this direction, and so I've kind of got this terminal point here, that's choked flow, where I've got Mach 1. That means if I was to try to add more heat here, it just won't go in. So for example, you could imagine, let's look at this diagram over here. If I had flow coming through that was exactly at Mach 1, and I tried to heat it, so maybe I was shining a heat lamp on this, that heat actually would never get into the fluid. It would just go ahead and build up, and the wall of this pipe would get hot, but I cannot get the heat into that point. I'm over here, and since heating goes in this direction and heating goes in this direction, there's no way for that heat to get in there. It's a really, really interesting situation, what goes on with choked flow. Okay, so qualitatively, that's what goes on with heating of fast fluids. And now what I'll do is go through a couple examples. And so first what I'm going to do is let's go ahead and solve example 1715, but I'm going to do it with EES because I think it helps elucidate what's actually going on. And then I'll go through another example problem where I'll go ahead and solve using the table. But first, let's just go ahead and look at exactly what we're doing, because the thing I want you to remember is all we're solving is a mass, momentum, and energy balance equation to find our outlet conditions for our inlet conditions. So here's the example problem from the book. This is an inlet pressure, temperature, and a velocity that are given right over here, and it wants to go ahead and find out the outlet conditions. And the other thing it tells you is that it's being heated, and what it's doing is we've got essentially an air fuel mixture is what's going through this pipe. It's got a lower heating value of the fuel of 42,000, and they tell you the air to fuel ratio is 40. The air to fuel ratio is the mass of air to the mass of fuel. So the first thing is we're going to use this to go ahead and find out what is Q dot. So to find Q dot, and the units on Q dot, remember this is going to be something like energy, not kilojoules per kilogram, but this is per kilogram of air. And so that's what I'm trying to find given here. And so what I do is I'm going to take my lower heating value, because that's the amount of heat per kilogram of fuel, right? And then I'm going to go ahead and divide that by the air to fuel ratio, because the air to fuel ratio is the mass of air to the mass of fuel. And this is per mass of fuel. And what that's going to end up giving me then is going to be amount of heat. And now it's going to be per mass of air, which is Q dot. So all I need to do is take my 42,000 and divide it by 40. So if I take 42,000 and divide it by 40, I get 1050. And that is now going to be kilojoules per kilogram. And that's going to be a kilogram of air. That's the Q dot that appears in the energy balance. All right, so there's my 1050 value. Okay. Now, let's go ahead and look at this diagram here in the lower left and remember what we're doing. This is all my possible solutions for various values of Q. I know Q, it's 1050. If we look, actually, our inlet velocity is 80 meters per second. That's actually pretty slow. So I'm probably up on this upper curve right over here. I'm adding 1050, so I'm going to some point, and the question is, am I there? Am I there? Am I there? And I can't get any farther than A. We know that. But I'm going to go up to some point over here. And since it tells me I'm actually able to add this much heat, I'm going to be somewhere between point A and here, but I could be anywhere along that curve. And that's what we're going to solve for. We're going to solve for that point by using our combined mass, energy, and momentum balances. So let's go over to EES, because I think it helps make it really clear what we're doing, because you kind of need to solve all these equations simultaneously. So here I've got EES, and first I'm just going to find some properties of air, where I've got my heat capacity and my value of R and K. And one of the things to note is since we're doing Mach number calculations, a lot of times I'll want this in joules per kilogram Kelvin so I can get my velocity in meters per second. So be a little careful on the units there of CP and R. I've got 1005 and 287. Here's the inlet conditions that were specified. Temperature of 550, pressure 480, and a velocity of 80 meters per second. And so what I'm going to do is I'm going to find my Mach numbers. This is just more out of an interesting thing to find out how far we are to Mach 1. And so remember, the Mach number is just divided by the square root of kRt, and so which is the speed of sound. So I've got my definition on Mach number 1 at the inlet and the outlet. And then what I have is my single energy balance. So I have my heat addition, Q, and then what I've got is the energy, which is Cp times T, heat capacity, and then the velocity term. So my enthalpy term and my kinetic energy term. Cpt is enthalpy. V squared over 2 is my kinetic energy term, and that's the outlet. There's no heat at the outlet term. I'm adding it to the inlet. Here's my momentum balance, the pressure times the density I'm calling rho, times V squared. And we saw this energy balance, or sorry, this momentum balance on the previous slide. And then my mass balance, which is rho times V. And so note here, V is velocity, not volume. Last thing I'll need to do in order to get those densities, I've got my ideal gas law at 0.1 and 2, and that's just P over RT. And then the last thing is I'm specifying my value of Q, because that tells me where 0.2 is. This is going to tie 0.2 to 0.1. It's 1050, and I've got to express that in joules per kilogram because of the way I wrote my energy balance over here. Let's go back and look. CP, remember I did CP in joules per kilogram Kelvin. It was 1005, so I need to keep those units constant. And so that's going to go ahead and give me Q. All right, so I'm going to go ahead and solve this. And I have to solve all three of these simultaneously in order to get my outlet conditions. So let's go ahead and see what solutions we've got here. And EES found a solution. And if we go ahead and look at this, just a little sanity check, notice, ooh, wow, that doesn't look weird. It looks a little strange that the outlet temperature is 0.000 in Kelvin. That's essentially absolute zero. That doesn't seem to make any sense. If I was heating a subsonic fluid, I should get hotter. So now I need to help EES out a little bit here. So what I'm going to do is go to my under options, I'm going to go to variable information, and I'm going to go ahead and help EES find what would be the more likely solution, which I know my temperature should be more, at least like 1,000 degrees. So I'm going to go ahead and have it guess 1,000 degrees for what T2 is, and let's see if we can get a solution that makes a little bit more sense. And so if I look here, and 554, that's still not warm enough. So I think that I've got a typo in my equation. Oops, I have a typo in my energy balance. If you look at my energy balance there, I've actually, unfortunately, got a multiplication sign instead of a plus sign. So let me go ahead and fix that. There's +2. Let's go ahead and solve this now and see what we get. So, okay, this makes more sense now. All right, so now if I look at my outlet temperature, an outlet temperature of 1567, that's something that makes more sense and actually agrees with the example problem. So if I look at my pressure, it's gone down 438, and I can go ahead and look at my Mach number. I started on Mach 0.17, and I went up to Mach 0.3. So let's go back and look at our diagram, just get a kind of qualitative idea. We started at Mach about 0.17, and we went up to about 0.13. So we more or less moved along the curve in that direction right there. Okay, so hopefully what you saw from that is by writing out those energy balances, mass balance, momentum balances really clearly, we see all we're doing is solving for that by specifying what Q is. Okay. Now the other way to do this is to solve it using Rayleigh tables, which are very similar to the shock wave tables we looked at in previous videos. So let's go ahead and look at another example, and I'll go ahead and solve it using the table. So here's a problem we're going to solve. Now I have air, and my inlet conditions are 300 Kelvin, 420 kPa, and a Mach number of 2. And I'm heating it, and here I'm giving what the heating rate is, and I'm asked what the outlet conditions are. So I'm just kind of explicitly giving Q. So in the last problem, we sort of had it. We had to calculate it. I'm just going to already calculate Q dot at 55 kilojoules per kilogram of air. So now my inlet is Mach 2. So if I look at this diagram now, I'm supersonic. So I'm some point down there. And remember, if I'm heating, I'm going to be going this direction. So I'm going to be getting warmer, but I'm going to be going slower. So I'm going toward Mach 1. So we're going to go ahead and solve for that condition, and we'll do this one by hand and using the Rayleigh tables. So first we need to find out what inlet conditions are, and so we're told at Mach 1, so let's go ahead and find out what our speed of sound is at the inlet. Remember, the speed of sound is the square root of kRt. So if I go ahead and put in kRt for air, and I know what my inlet condition is, that's T1, that comes out to be 347.2 Kelvin. All right, so there's what my speed of sound is. So then I can go ahead and find out what, for example, my stagnation temperature is. And what we're going to do, let's go ahead and find our stagnation temperature, which is T01. And that's just going to be T1, that 300 degrees right there. And then remember, we add our velocity, V1 squared. That's V1 squared over 2Cp to find my stagnation temperature. And that's going to be 300 plus my 347.2 times 2, speed of sound times Mach 2. That's my inlet velocity, and my 1005. And then there's a factor of 2, and I need to go ahead and square that thing on the upper range. And that number comes out to be 540 Kelvin. So there's what my inlet stagnation temperature is. So then what I'm going to use now is my energy balance. My energy balance tells me if I take my stagnation temperature, T01, and now I'm going to go ahead and add heat, Q dot over Cp, that's going to be T02. And just to kind of clarify, by doing stagnation temperature here, remember this last time I explicitly wrote what H was and then my kinetic energy terms when I did this in EES. Now I'm calculating stagnation temperatures, T01 and T02, because these are what appear in the Rayleigh table, so it'll make a little bit more sense here. So now I'm going to go ahead and plug my numbers in here. I've got my T01, that's 540. Q naught is given at 55, and Cp is a constant, so I can go ahead and find out what T02 is. And if I do that arithmetic, T02 comes out to be 594.6. So there's what the stagnation temperature is at the outlet. So more or less I'm told where I am now in terms of stagnation. Not absolute temperature, but some point at stagnation temperature here. So what we're going to want to do is figure out where it is. This is where the Rayleigh tables come in. And so what we're going to look at is a Rayleigh table. So let's go ahead and look at the Rayleigh table and see what's on here. So this is the very last table in the book. It's table A34. And so this right over here is a listing. We look on the left-hand side, Mach 0 to 3. So you can think of this is like all those points along that curve. So if I think of my curve here for T and S, right, I'm going in this direction. More or less what these points are over here are all just points on this curve. And so what we're going to be doing is finding one point and finding another point that's connected with Q. Okay, and what it gives me is values over these with a star. And the values with a star are the choked flow. Those are the values of this point right over here. So that's my star value. And so more or less what this is a table of this value relative to this point. And then I can go ahead and connect that with my energy balance to find out where my point 2 is. But again, it'll always be relative to T star. So, or T star or P star, or whatever we're using. So we're going to go ahead and be finding values at that point. Okay? So what we can do is, let's look over here. Here we're at Mach 2, so this is this line right over here. All right, so those are what my inlet conditions are. So what tells me is, for example, my inlet stagnation temperature over T star is going to be 0.7934. So from that I can find T star, and then I can use that to find my outlet conditions. So let's go ahead and just go back and do that map there. So stagnation temperature T01 over T0 star. And that was, well, we found 540 up top. That was my inlet stagnation temperature. I'm solving for what is T star. And from the table at Mach 2, I saw that was 0.7934. So that was from the table. And now what I can do is solve this equation for T naught star. So T naught star is then going to be equal to 680.5. And the reason is this is this constant value. So now I've got my outlet stagnation, T02 over T star. Okay. Well, I found T02 right there. I'm going to plug that into that. Here's my T star and plug that into there and get a value which is 0.874. I'm calculating that. So then this 0.874, I can go ahead and find out what my outlet conditions are by returning to the table. So remember, 0.874. Let's go back to our table over here. And so 0.874 appears somewhere between, for example, those two values there. It's going to be pretty close to, for example, this number 1.6, and so it's going to be a little bit more than 1.6. And so from there, I can go ahead and figure out what my Mach number is. I'm just going to go ahead and maybe linearly interpolate that, and I find out that my Mach number 2 is equal to 1.64. So there's what my outlet Mach number is. And so from there, I can, for example, find some other outlet conditions. So let's say, let's go ahead and find out what our outlet temperature is, just to kind of use this table one more time so you kind of see what's going on. So what I'm going to do, I'll go back to my table here. Now we'll go ahead and find our temperature. So instead of using stagnation temperature here, I'm going to be using the absolute temperature, T over T star. So let's look at what we want to do. Okay, so once again, what I'm going to do is now I'm going to take my inlet condition, T1 that I know, and I'm going to go ahead and solve for what is T star, the point at choked flow. The inlet was told I was at 300 Kelvin, and I'm solving for T star. And so what's that ratio? So again, I do that at the inlet. So let's go ahead and look at my inlet. Mach number is 2, and so that's going to be 0.5289, this value right here, that is the ratio. So 0.5289. And now I'm going to go ahead and solve for what is T star from there. And so T star, the temperature of my choked flow, is going to end up being 567.2. And now I can go ahead and find T2 over T star. Right? I want to solve for what is T2. I know my T star, that is 567.2. And then that, I need to go ahead and determine, well, let's go back to my table here. Remember, we're somewhere in between these two lines. And if I come over and interpolate to figure out where I am at this point as well, using that same interpolation, I'd be about, if I do that, it's about 0.682. So remember, Mach 1.34, 1.64. And now I can go ahead and solve for what is T2, and T2 comes out to be 386 Kelvin. So now I'm finding out what my outlet temperature is given what my inlet is. That might be outlet 2, inlet at 1. Okay? So hopefully you can see you can go ahead and determine your pressures if you wanted to figure out your outlet pressures. If you want to find, now that I know the temperature, I could go ahead and determine what the speed of sound is. That's going to be the square root of KRT. And I can determine, for example, what the Mach number is at there as well. So, okay. I think that's it. So hopefully that sees how to use the Rayleigh table.